All right, we're back. This is basic statistics. We're looking at chapter 3. We're doing 3.2, measures of variation. So that's how varied the data is. Let's pretend we had a real boring set. What if I had a set where it was all sevens? Just 7, 7, 7, 7, 7, 7, 10 sevens. There'd be no variation. The standard deviation would be 0. There's no deviation from the mean on any one of those numbers. The mean would be 7, the mode would be 7, the median would be 7. So everything is 7, and then the standard deviation is a measure of spread. It's how far away each piece of data is from the mean of the data. And so we're going to take a look at variation. So it's measure of variation or measure of spread, how spread out the data is. First one that's the easiest is the range. So if you look on chapter 3, page 6 of the note packet, 3.2, measure of variation, they want you to find the range. And so when you find the range, we're just doing 70 minus 43. It looks like it's the president's ages again. So that's 27. Just the highest piece of data minus the lowest piece of data. That's it. That's the range. And so the one below it there, it's height in inches. And that looks like it's got the exact same range, but there's a lot less variation. So that's why we can't just use range. 70 minus 43, still 27, so 70 was still the high, and 43 was still the low. But unlike the president's age, where it's kind of all over the place, this one is really tightly knit it looks like it's really around the 60s. So it's grouped together more closely. So if we looked at standard deviations of the two sets, that would separate them from each other, as one is more varied than the other, where the ranges are identical. So watch out for range. It can be a little misleading. It is a measure of spread, but it isn't. It doesn't tell us a lot about the data, or as much as like a standard deviation does. So when we calculate the variance for a population of size n, we're talking about population, so it's mu for the mean, and variance is going to be sigma squared. So when you look on the next page here, it's square these differences, add up the squares, divide by n. So when it's a population, you divide by n. When it's a sample, you divide by n minus 1. That's called degrees of freedom. And so that becomes an important distinction. So then on page 7 here, it tells you for the notation for variance is the standard deviation squared. So if we want the standard deviation, let's take a look at the variance first. The variance is the sum of each value, x, minus the mean. That's x bar. Oh, that's going to be mu though, because this is a population. It's sigma, so that means population. So mu instead of x bar. It's still the mean, it's just the mean of the population. You square the results, and then you divide by n how many pieces of data there are. If I want to find the standard deviation of the population then, well, if we remember any of our math at all from algebra, you just take the square root of both sides. And so that becomes sigma. And we got the square root of the summation, x minus mu squared, all over n. And n is under the square root sign. That was a real common error made last semester that I taught this. A bunch of students got that wrong because they had the n on the outside instead of on the inside. All right? If we look at samples instead of populations, it's almost an identical thing, but instead of sigma, the Greek letter, we use the English letter S squared. It's called the variance either way. This is just the variance of the population, the variance of the sample. And so that is going to be, it's going to look almost the same, except there'll be an x bar there. So that is the variance. And then if we take the square root of the variance, that gives us the standard deviation. And so that is the summation of each value subtracted from the mean. You square the result. You divide it by n minus 1. Oop, n minus 1. Ooh, I almost made the mistake here. When it's a population, it's n. When it's a sample, it's n minus 1. Oh, population, n is usually a capital letter, and sample, n is usually a small letter. And put the square root sign around that sucker. So this can be kind of tedious to find. I'm going to show you how to do it on Excel, and I'll also show you how to do it by hand. If you want to do it by hand, you could do it by hand. All right. So let's look at the page 8. So the Excel video will be a separate video entirely. I'm going to move ops up to the computer upstairs, and I'll walk you through how to do it on Excel with a set of data. We'll find the mean and the standard deviation, and I'll show you. You can do it for population or you can do it for sample. All right. So let's look at page 8. They talk about the coefficient of variance. The coefficient of variance, which is a pretty simple way to take a look to see which one is more varied, which sample would be a more varied sample, or population, I guess, if you had a whole population to look at. And so the coefficient of variation, what you're doing is you're dividing the mean by the standard deviation divided by the mean, rather. Standard deviation divided by mean. And that'll give you a percent. And the bigger the percent, the more variable the data. And so it's a pretty easy way to find it. So look, they said for heights and weights, find the coefficient of variation, the C-bar. And so let's take a look at that. For height, the mean, if you add up all those values and divide by how many there are, it's 63.9. The standard deviation, what you do is you take 63.9 subtracted from each one of those values, square the results, add them all together, divide by n minus 1, and then take the square root of it. That would give you the standard deviation, 9.62. I'll show you how to do that on the computer on Excel. All right, so that's for height. For weight, X bar, that's just adding them all up, dividing by how many there are. 146.5 for the weight, and the standard deviation, 48.26. And these are rounded values. It went on past hundredths place. We rounded to hundredths. And so now, if we look at the C-bar, the coefficient of variation for height, for weight, that would be 9.62 divided by 63.9 times 100 to make it into a percent. And so we're looking at 15.1% for height. And then for weight, we've got 48.26 divided by 146.5 times 100 to make it into a percent. And that's 32.9%. And so if I asked which one is more variable, that would be weight. Weight is almost double the percent, right? So this one is more variable. Weight is more variable than height. All right, and then there's sort of a general rule that the standard deviation of data set is about 1/4 of the data. Like, it usually splits the data into quarters. That's not always, but in general, it's a quick way to get a quick estimate. So if you take the range and divide it by 4, that'll give you an approximation for it. So on height, for the data above here, if we take the range and divide it by 4, that's 40 divided by 4. That's 10. And we did find the standard deviation of height to be 9.62, which is pretty close to 10. So in that case, was pretty close. The real standard deviation there. Wait, I don't think that one is going to work as well. We're going to take the range, which is 168, and divide that by 4. That's 42, and it was actually a little closer to 50 than to 40, so the actual one isn't very close for weight. And so that's why that's just a kind of a general rule. We don't really use that other than just a quick way to get an estimate for the standard deviation without doing all the calculations or entering in all the data. Chebyshev's theorem is 1 minus 1 over k squared times 100%. The data will lie within k standard deviations of the mean. And so when we take a look at that, let's look at page 9 of the note packet. We're looking at specifically k equals 2 at 75% of the data lies within 2 standard deviations. So let's check that Chebyshev's rule. And I think that's for any set, whether it's normal or not normal, works with any distribution of data. So it doesn't have to be normally distributed. It'll work for anything. In the case where the data is a nice shape, we can do even better. Okay, so let's see here. K equals 2, K equals 3, K equals 4. And that's at least 75% or 88.9% or 93.75%. So let's go through the steps here for heights. So this is for heights. Number 1 is, we know the mean was 63.9 and the standard deviation, it's for a population we're doing it. So the mean is the same as x bar. But for standard deviation, we're going to divide by n. So that's going to change to 9.29. In Excel, that's standdev.p instead of standdev.s. S for sample, P for population. So we're doing it for the population. So find the length of 2 standard deviations. So we got 2 times 9.29. That is 18.58 units. And so now what we're going to do is find the interval that corresponds. So the mean, look, if it's a normal set of data, we don't know that it's normal. This could be any set. The 63.9 is right here, and then we're going to go 2 standard deviations above and 2 standard deviations below. So we're going to take this 63.9 and subtract 2 standard deviations below and add 2 standard deviations above, and that'll be the set. All right, so 63.9 minus 18.58 and 63.9 plus 18.58. And again, if you came from algebra, you'll understand this as set notation, right? 45.32 to 82.48. That's what that's not a point like on X and a Y. That's it begins at 45.32 and goes to 82.48. And so now if we take a look at the data, how many points, how many of the height data falls between oops, that's number 4 here. 45.32 to 82.48. It's almost all of it. There's only one that got outside of there on the low end. And so 14 of the 15 pieces of data. And so now let's do a proportion here. 14 of the 15 pieces, 14 divided by 15, is 0.9333. So 93.3%, which is greater than 75%. And so Chebyshev's rule was it would just be greater than 75%. And it is. 93 is bigger than 75. So So it holds true for that. If we have a bell-shaped curve, we can do it with a little more precision than this. And that is the 68, 95, 99.7% rule. So and so what we're looking there is 68% of all the values would be between, and then we go 1 standard deviation below and 1 standard deviation above. So just what we did here, we're going to do it again for 68%. We're looking at the 63.9 minus 9.29 and the 63.9 plus 9.29. And then we already did the middle one. That's 95%. It's supposed to fall into that. So we did that one already. It's 45.32 and 82.48. And then the last one, the 99.7, that should capture almost all the data. That would be 3 times the 9.29 and subtracted, and 3 times the 9.29 and added. And so then you would get this interval from 36.03 to 91.77. And so, and this one was 54.61 and 73.19. And so when we look at that, it's if it's truly normal, we should be able to count up the data that falls into each one of these intervals, and it should be really close to 68, really close to 95, and really close to 99.7. And it's not super close. 93% was in this interval, and it should have been 95%. So we could make the assumption it's not normal based on that. We should really look at all of the data points before we jump to non-normal or close to normal or not normal. But the idea is that you understand one standard deviation above and below the mean captures the middle 68% of the data in a bell-shaped curve or a normal curve. If we go 2 standard deviations out, that will capture 95%. And if you go 3 standard deviations out from the mean, from the middle, this is the mean, that should capture 99.7%. Almost 100%. All right? So now let's look at measure of position, section 3.3. We're going to talk about Z-scores. So Z-scores, again, with populations. That Z-score, all a Z-score is how many standard deviations above the mean or how many standard deviations below the mean are we. So when we talk about Z-scores, we're talking about standard deviations above or below the mean. And so Z-scores are just standard deviations above or below the mean on a normal distribution. So when we look at Z on page 10, right in the middle there, Z is equal to X minus mu over sigma. That is a population. If we look at a Z for a sample, it's minus X bar and it's over S. And so remember, populations use Greek letters and samples use just English letters. All right? So let's find the statistics. Suppose you score 65 on a stats test with a mean of 50 and a standard deviation of 10. You also took an English test and scored a 30 with a mean of 25 and a standard deviation of 5. Which one did you do better against the class, relative to the class? Well, let's see. For stats, we have a Z-score of 65 minus 50, over 10 is how varied it was. So we're looking at, what, 15 over 10, 1.5. So you were 1.5 standard deviations above the rest of the class on that one. So you did good. For English, the Z-score, and a lot of times you could use a sub-letter here to differentiate between the two Z-scores. You could put a little S there for stats, and a little E there for English. So if you look back at your work, you know that one was stats and that one was English. Or you could just write stats and English and leave them both Z. Either way is fine. So 30 minus 25, but that wasn't as varied. That was only by 5. And so 5 divided by 5 is 1 standard deviation above the mean. So you still did good, but you're only 1 standard deviation above the mean. Where in stats, you were 1.5 standard deviations above the mean. So if you compared, how did you do? You did better than the average in both classes. But in stats, you were at a higher percentile ranking than in English. And so you did good in both classes, but you were further above average in stats. Average in stats. All right. All right, let's look at page 11, percentiles. So when we talk about percentiles, page 12, oh, we might have to do a part 3. Let's see how much time we got on this video. Oh, that's 21 minutes. So we'll do a part 3 for chapter 3, part 3 coming soon.